recording now, and let's think back to where we left off in our lecture from last Wednesday. We are still talking about, we're still going through our vector and coordinate system chapter. That's mostly review and kind of taking a moment to solve some practice problems. So let's get that presentation back up and running, and we can do a kind of brief review. Hold on, what do you want me to do? All right, so let's get rid of this. And then we can pull up our OneNote from chapter 3. We've been solving problems as we go along. Let me log in here just so I don't have to spend so much time going back and forth. Let's see, I want to join. Okay. All right, let's start sharing here. So just brief recap from a week ago, we had, we spent some time talking about vector representations in general. We had a little taste of this before we got to this chapter, specifically when we were learning to make motion diagrams. And we started off with position vectors. We could use those to determine what orientation and magnitude displacement vectors had. And then our next step was to turn those into velocity vectors. So we had one example from, I want to say, chapter 1, where we had a position vector that was described just as the one that we see here in this example with Sam taking a hike. So the distance, or the, I guess the separation between the starting point and the end point is the magnitude. And then when it's paired up with this, a direction where northeast, southwest, anything like that, that is implied to mean a 45-degree angle. So the bisector between those two cardinal directions. Now we have Bill, who is undergoing, doesn't necessarily have to be exactly the same hike, but they both end up 200 feet northeast of their front doors, so we can treat vectors B and S as being the same. We talked about how we can add vectors together using either tip to tail or the parallelogram rule. I tend to default to tip to tail, but if you default to parallelogram, that is completely fine. I have no like demands about which one of these you need to use. We talked about the Pythagorean theorem and how we can use that to figure out like the total displacement of a chain of vectors that you add together. In this case, just vectors A and B, the hypotenuse is C. So in this example, we've got a 3, 4, 5 right triangle. We could use that to define one of these interior angles. More often than not, the interior angle is going to be defined as theta, and it's going to be given with respect to the x-axis. But we saw some examples later on in this chapter where that does not need to be the case. So we did some practice problems. These here, we talked about vector multiplication by a scalar that has, or it serves the function of only stretching or shrinking a vector. It can't change the direction of the vector. You did some more on these. Then we started talking about component vectors. So another way that we can express exactly the same type of vector that we saw with the example of Sam taking a hike a bit earlier. But now we're expressing this vector A as the sum of two component vectors, AX and AY, where when added together, they're going to give us this hypotenuse. And kind of more importantly, if we're given a vector A, we can break it down or decompose it into components AX and AY. We did that for a few sets of practice problems. We have, not here, but here. This is our example of how to go back and forth between geometric and component representation of vectors, because it's not always convenient to draw a vector and add it to another one. Sometimes it's a lot more convenient to add by components. So in this case here, since we have our interior angle theta defined with respect to the horizontal, the magnitude of the component vector AX is going to be a cosine theta. And then we can say that the magnitude of AY is going to be a sine theta. But it's not safe to always assume that cosine is always horizontal, sine is always vertical. In the case here where we have an angle phi that is defined with respect to the y-axis, now the cosine component gives us the by component's magnitude, and the sine gives us the bx. So let me jump back over to OneNote here so that we can see where we left off, because we worked through a good deal of these last time, but not all of them. And it looks like we finished up with examples 13 through 15. So we did these here. We wanted to figure out the magnitude of these vectors, or these vector components, and we wanted to kind of show how they are oriented with respect to the X and Y axis. So let's, yeah, okay, so let's quit sharing here, and I'm going to switch back over. Okay, here's where we left off last Wednesday. We have vectors A, B, and C that we decomposed into X and Y components. And in each case, we were given an angle, sometimes with respect to the positive X, sometimes with respect to negative X. And we found that we can not only figure out the magnitude of these components, but use a negative sign when necessary to indicate whether that component vector is pointing along negative X or negative Y, as is the case for AX in problem example 13, for BX and BY in problem 14, and then just for CY in 15. So let me see, we did 13 through 15. So the next slide in our presentation is 16 through 18. Now we're going in the opposite direction. We're given information about the magnitude of the component vectors, and we want to figure out how to draw that vector and what its magnitude should be. So to stay consistent here, I was using red for X, green for Y. I'll keep doing that. So for the case of 16, AX is positive 3. So there will be my AX component vector. And let me do this so I can see exactly what you see. Okay, that's better. So BX, I'm just going to continue all with the same color so I don't have to go back and forth. Since BX is -2, it's going to be coincident with the negative x-axis. CX is equal to 0. So the vector C that we build is going to be fully captured along the y-axis. Now, I might as well start with CY. CY is -2, BY is +2, AY is -2. So using the parallelogram method here, I know that vector A is going to be the sum of these two. Vector B is going to fall in quadrant 2. And then vector C, I'll draw off to the side, but it is exactly the same as CY. So now we can work on the second part of this. So the the magnitudes. We are going to use this here. So it's essentially the Pythagorean theorem. C squared is equal to A squared plus B squared. So for vector A, if I want to find the magnitude of that hypotenuse, it's going to be AX. So this is positive 3 quantity squared plus now negative 2 quantity squared. So the square root of 9 plus 4. So radical 13, which is about 3.6. And all we have to do is do the same for vector B. We won't have to do the same for vector C for obvious reasons. I'll do the calculation anyway, but you will kind of spot the pattern before I get there, I'm sure. So BX, that's negative 2 quantity squared added to positive 2 quantity squared. So the square root of 4 plus 4, which is radical 8, which is about 2.8. And then for vector C, we have 0 quantity squared added to negative 2 quantity squared, all that underneath the radical. So this is going to be the square root of 4, and that'll just give us a 2. So not a shock, because vector C is completely constructed of vector component cy. I'm adding it to a 0 vector. So the magnitude of cy is also going to be the magnitude of C. Okay, so let's swap. And now we are here. All right, so we are now looking at a different, so another method that we can use to communicate the magnitude and direction of any vector. And this is making use of unit vector notation. So we have the first quadrant shown here with the I hat unit vector pointing along the positive x direction. It's just got a magnitude of 1, so that it really can't change the length of the vector that we are describing along this axis. It really just exists to indicate the direction. J hat does exactly the same thing for the y direction. It's not shown here, but K hat does the same thing for the z axis. So they line up with the positive part of that axis. That gives us, let me jump forward. No, I thought that I had an additional slide here. But this gives us kind of our first taste of something that is going to recur in Unit 3 and again in Unit 4, I believe, when we're talking about I guess this is just only Unit 3 now that I think about it, but cross products compared to dot products. And I always forget whether this is something that's discussed in Calc 1 or 2. So some of you might be hearing it or encountering it for the first time here in this context, and then you might end up discussing it a little bit later on if you are taking Calc 2 concurrently. I want to say it's in Calc 2. But this is going to become relevant when we are discussing torque and energy. But for our purposes right now, these unit vectors just pretty much exist to indicate the direction of the positive x, y, and z axes with I, j, and k. We'll worry about combining vectors or combining unit vectors a little bit later on in our semester. So let's look back at this same generic vector A that we decomposed into an AX and an AY a few slides previously. We can now change the way that we communicate how, or the way that we describe a vector AX and vector AY in terms of this product here. So the scalar portion, AX, is just the magnitude of that vector. I hat is just 1 times this unit vector, or really 1 times AX in the direction of this unit vector. So we can say AX in the I hat direction plus AY in the J hat direction gives us this vector A. And anytime you have vectors that are expressed in unit vector notation like this, you can add them directly the same way that we see here. So for the case where you are dealing with an object that might be moving along the X, Y, and Z axes, all you would have to do is just add an additional term here. So you would have a X in the I hat direction added to a Y in the J hat direction added to a Z in the K hat direction. So let's take a crack at these problems. We've got 19, 20, 21, and then we'll go straight through to number 25. So I'm going to swap over and we can solve these. Okay, so we want to draw and label, and I'll use the same color coding. I'll do all the X's first in red. So 19, I have minus I hat, so -1 times the I hat vector. It'll be like this. There's no X component for B, so I'm going to skip over. And if we look at vector C in number 21, I have a +3 in the I hat direction, so this is going to be CX. Then I'll come back and fill in the Y's. So back to 19. 2 times J hat means that the Y component of A is going to be coincident with +Y. For vector B in number 20, it's going to be coincident with -Y. And actually vector C has exactly the same Y component as vector B did. So now our last step is just to add these together. And I'll use the parallelogram method because it's the most straightforward for this particular example. Vector B is going to be completely coincident with the BY vector. So in other words, I'm adding a 0 vector to BY, and I just end up with the same thing that I started with. And for vector C, we end up with a vector that's pointing into quadrant 4. We're not asked to calculate the magnitude for this set, but we could using exactly the same procedure that we did for the last trio of problems. Okay, so 22 through 24. Now we're working in the opposite direction. I'm going to decompose all 3 of these vectors into X and Y components. And in the case of vector C, again, I have one that will yield no Y component. So I'll say CY is equal to the 0 vector. And my goal here is just to write these in unit vector notation. So for number 22, I have +1 times I hat added to +3 J hat. You could drop the 1 in front of the unit vector. I'm just keeping it here because I'm just kind of still getting started with this topic here. For B, I have -1 I hat plus, and I'll say -2 J hat. Back up here, -2 J hat. And then for C, I have -3 in the I hat direction, and I'm going to add it to 0 J hat. So anytime both of your unit vectors are Oh yeah, thank you for that. I put in the chat. I did write that backward for number 22. So let's fix this here. This should be x first. So 3 I hat added to 1j hat. Thank you for pointing that out. Make sure the others are still good. Yeah. Okay, so that would have messed up our response to number 25 because now we just want to add all three of these vectors together. So if we stick with our component form, vector D, I'm going to take all of the components for the x direction, add them together, multiply them by the I hat unit vector. So this leaves me with 3 minus 1 minus 3. And instead of a square bracket, let me do this. All that in the I hat direction. Added to, now I have a 1, a -2, and a 0 in the j hat direction, where these are just the magnitudes. All right, so 3 minus 1 will give us a 2 minus 3. This is going to be -1 I hat. And then I'm adding that to my j hat component. So 1 minus 2, this is also going to be -1 j hat. So we're not asked to draw it, but we would end up with a vector that points into quadrant 3. This would be our vector D. This would be -1. This would also be -1. Okay, so we're going to switch back. Okay, so we did 19 through 21, went straight through 22 to 25. So just to recap, the method that I used to figure out what vector D needed to be just involved me taking the magnitudes of all of the x component vectors, dealing with them together, and then doing the same thing for the y values. If I had z-axis components, I would just add those together as well. And I didn't really talk about it here, but in our lecture from last Wednesday, we talked in more detail about subtracting a vector from another. So for example, if vector r is p minus q, all I would need to do is identify vector q, invert its direction so that it's 180 degrees different, but the magnitudes are exactly the same. And I can take vector p and add it to -q. That would be exactly the same as taking p minus q. If instead of just adding a bunch of vectors together, if I had now some generic vector s that I was multiplying by some scalar c, the thing that we would have to keep in mind is that c is incapable of changing the direction of vector s. It's just going to stretch or shrink the magnet or the length of the arrow. So the magnitude is all that can change. And I can just distribute this amongst both terms exactly the same way that I did when I was just doing addition or subtraction. All right, so now we have another group of 3 problems, so 26 through 28. We're given the vector in unit vector notation. We want to draw this vector, label an angle theta so that we can describe the direction, and then find the magnitude and direction of that vector. So here we go. Let's quit there. Start here. All right, so we've kind of got the hang of how these component vectors go, so I'm going to skip drawing the x and the y separately and color coding them, and I'll just go straight to vector A. So for vector A, I have positive 2 I hat, positive 2 j hat. That tells me this is going to fall in quadrant 1 because they're both positive. For case B, I have a negative I hat component, a positive y or j hat. So that's going to be quadrant number 2. And I've got positive, positive for vector C. So I know that's going to be quadrant 1 again. But I'm going to have this vector now. So I'm going to draw my angle theta for vector A here with respect to positive x. So that, again, is just an arbitrary choice. There's no reason you couldn't have drawn this with respect to positive y. But for this specific angle theta, I can then use the inverse tangent to determine the value of theta. So to stay in order, I'll do the magnitude first, and then we can go back to calculating the angle theta. So the magnitude here for vector A, that's going to be the square root of positive 2 squared plus positive 2 squared. We know that this is radical 8, so that's like 2.8. And now for theta, if the tangent of theta is opposite over adjacent, opposite being positive 2, adjacent also being a positive 2, this gives us a result that you probably already guessed. This theta is going to be the inverse tangent of 1, or the arctangent of 1. So that's 45 degrees. For vector A, if you looked at this and you decided to draw your theta with respect to y, you would come to exactly the same conclusion. We also already know that this angle theta is also going to apply to vector B because the x and the y component have the same magnitude. So I'll draw theta with respect to the y-axis this time, just for the sake of variety. But I'm going to end up with a magnitude that's exactly the same as we had for case B, or excuse me, vector A. So this is going to be negative 2 quantity squared added to positive 2 quantity squared. That's still radical 8. And this angle theta here is going to have a magnitude of 45 degrees. But at this point here, and this is kind of, I think, a personal preference thing, the manner in which you kind of indicate or confirm, really, the choice that you made for angle theta, you can do this different ways. So one way that you could do this is to say that theta is going to be the inverse tangent of opposite over adjacent, opposite being negative 2, adjacent being positive 2, so that this would yield a negative 45 when you calculate that. That is okay to do. That's what you would get if we instead drew our angle theta with respect to negative x. We would get a negative sign that shows up there as well, simply because of that ratio between negative 2 and positive 2. You could, let's say if this was an exam, you could say that this angle theta is 45 degrees measured with respect to positive y. That would be valid as long as you were telling me, giving me some sort of indication as to where to place your angle theta. Because if you imagine that you just handed me a 3x5 card, let's say, that had these information on it, just telling me that it's a 45-degree angle is not enough to tell me which quadrant it should go into. So as long as you try to communicate that however you choose, I'm not picky about that on exams. And then for C, now we have 3 squared added to 1 square. So radical 10 is what value? About 3.2. And I will choose to draw my theta with respect to the x-axis so that theta is going to be the inverse tangent of opposite over adjacent, opposite being +1, adjacent being +3. So we are going to end up with, oh, I need to be in degree mode for this, about 18 degrees.
I just wanted to clarify because you mentioned about having to indicate the quadrant for vector B. Is that only having to be done when we get a negative angle, or every time that we take a test you want us to indicate the quadrant?
You don't always have to indicate the quadrant. Like in an exam, I'll usually give, or I'll ask you to give your angle with respect to positive x or something like that, just because it's easier for me to grade quickly if we're all using the same reference point. But if this were, let's say if you were the only student in the class and I didn't have a stack to work through all the time, it's perfectly okay to say that that angle is -45, because that would be true with well, I do have enough information to determine that this has to fall into quadrant B, or sorry, not quadrant B, quadrant 2, because vector B is 1 positive, 1 negative, so a negative x, a positive y is going to give us quadrant 2. But that's just a long-winded way of saying, no, you don't always have to write down like what quadrant it is. As long as we are clear about which angle or which axis we are using as our reference point, I'll take, either one of these. Whichever one you like the most, as long as it's correct and I can follow your logic, it's good. All right, so I think we need to switch back, I think for one of the last times. And the last thing that we have is a topic that's pretty similar to what we encountered at the end of chapter 2 when we were talking about motion along an inclined plane. So let's, come on. Okay, there we go. Okay, so we encountered a tilted axis when we had that discussion about motion on an inclined plane. We mostly used it so that we could decompose an acceleration vector. So if we had an object that was sitting on a ramp, that ramp was inclined some angle theta above horizontal, we knew that the free fall acceleration vector was going to point straight down, but there's a component that is parallel to the ramp that would be equal to g times the sine of angle theta. It could be plus or minus based on whatever decision you make about your coordinate system. But that angle theta was our clue as to how we could break down that acceleration vector. And for any problem, like I think there's a homework problem about a hockey puck sliding up an icy ramp, and you want to figure out how far up the ramp it goes before it comes to rest. It makes a lot of sense to draw your coordinate system so that it or one of your axes coincides with the actual trajectory of the object. And that is what we did in that practice problem about a ball rolling down a ramp at the same time that one was moving horizontally. And it's a good idea to apply if you are instead just working with vectors as opposed to, I mean, we were mostly paying attention to the magnitudes of the quantities that we were given to solve that problem, but it's something that also works for vectors as well. So let's imagine we've got some generic vector C, and we have chosen to put our X and Y axes like this. This is a completely arbitrary choice. There's no reason that I couldn't have made Y vertical with respect to our frame and X horizontal with respect to our frame. But now that I've made this decision about how the coordinate system is oriented, if I choose an axis, or if I choose an angle theta to use to decompose this, CX now is going to be described, or I'll say it this way, CX and CY are magnitudes that are kind of dependent on this coordinate system that I selected. So to rephrase that another way, imagine that I do just have a traditional Cartesian coordinate system where y is vertical relative to our frame, x is horizontal. The values that I would have for CX and CY would be different, but they would still yield a magnitude that is the same. Because changing around the coordinate system, or like the angle of the coordinate system, can't do anything to make this vector C longer or shorter. But it does change how theta is defined. And that can change how, or that will change how the component magnitude CX and CY compare to each other. So last but not least, we've got 3 more workbook problems. And let's swap. Okay, so we are given the same vector A, but in different coordinate systems. We want to figure out how AX and AY relate to one another. So let's start with 29 here. We have, and again, I'll skip the color coding part because we're 30 problems deep now. So AX, if I decompose vector A into my, my first coordinate system, this is going to be A times the cosine of theta, where that is going to be 5 cosine 30. So maybe I will not write this right here, but underneath. AX is A cosine theta. AY will be A times sine theta. So AX, the magnitude I know is 5. The cosine of 30 degrees is going to be multiplied by that. So 5 cosine 30 is about 4.3. And for AY, 5 times the sine of 30 degrees is going to give me 2.5, sine 30 being equal to 0.5. Now for number 30, this is exactly the same vector A, but a new coordinate system. So I have tilted this coordinate system 30 degrees relative to the original one, so that now I'm going to treat this as my angle. This would be 60 degrees now. So I'm still going to be using the cosine component to determine the x component of vector A. So the sine is going to be y. The magnitude is still 5, but now this is the cosine of 60 degrees, and then 5 times the sine of 60 degrees here. So 60 and 30 being complementary, cosine 60 is going to be 1/2, so this is going to be 2.5 for AX, and then sine 60 is the same as cosine 30. Sorry, let me move this off my screen. Okay. So then this is going to give me 4.3. Now 31, we have an X and a Y axis that are inclined even more now with respect to our traditional our Cartesian coordinate system. So I think I will take the opportunity here to color code some of these component vectors just so that it's clearer. So AX, I've been using red for X's. So AX will be here. And then AY will be here. So we've got a little work to do as far as determining which angles to use. Let's start with, say, this angle right here. That's probably not sufficient. Let's narrow this down some. So this angle needs to be 45 degrees. Just because my y-axis is intersecting the dotted line, which is horizontal, so I can find 45-degree angles on both sides. That tells me that this angle is also going to be 45 degrees because the x and the y coordinate axes are separated by 90 degrees. So I've got a 30-degree angle and a 45-degree angle. That's going to give me a 75-degree angle. So I know what remains here will be 15 degrees. So I'm going to use 15 degrees as the angle that I'm choosing to break these down. So for AX, AX will be A times the cosine of that angle. AY will be A sine. And it seems redundant, but I would suggest that you write out your AX and your AY each time because it's really tempting to think cosine is always X. It turned out to be X all 3 times here, but it is not a universal truth about all vectors. So always test. So we still have the same 5-unit magnitude, but now the cosine of the angle that I'm concerned with is going to be 15 degrees. So cosine 15, and then 5 sine 15, where 5 cos 15 is about 4.8, and 5 sine 15 is about 1.3. Now, let's see.
Does one of those have to be negative?
Yeah, that's exactly what I was going to mention, because we're kind of asked for the components of AX and AY. If I wanted to turn these into component vectors, then the negative sign is necessary. So it would be, let's see, AX would be 4.8 I hat. AY here would be negative 1.3 J hat. Okay. Any other questions before we switch over? Okay, if not, I'll stop sharing